Hey kids, so here we are at the last information you'll need before our quiz. And it starts with doing functions with significant figures. Now you might remember that significant figures are significant because they help us with estimations, right? So here with this beef, you know that it's more than 3 units and it's less than 4, and then you estimate one. So this measurement is only good to 2 decimal places. And we talked all sorts of things about that. So basically, when you're doing addition or multiplication or any other function like that with significant digits, you need to account for the fact that there are some weak digits in there and that this chain is only as strong as the weakest link. So you need to determine what that weakest link is and make sure your answer is not stronger than your least accurate measurement. And that is what we're doing. So addition and subtraction, the way this works is you want to line up where your, first of all, line up everything with a decimal point, and then establish where your least accurate digit was. So in this case, this 5.44, the point, oh, the hundredths place is where this number is the least accurate. The person who measured this, and estimated the 400ths place. So that is where that's the least accurate. And then the 2.6103, this person did a little more work in establishing an accurate number, but the 3 is where they estimated. So they knew this, they knew the 6, they knew the 1, they knew the 0, and they estimated the 3. So when you line these up, you can see that the 4 lines up here, the 3 much more to the right. So we have to, when we combine them, keep in mind that the least accurate is this 5, because the person who did this measurement with the 5.44 didn't even have a thousands or 10,000s place established. So the answer can't have a thousands or a 10,000s place. It has to stop here at the hundreds place. So right here with the 4, that is how accurate the answer is, which turns into the 5 when you do the addition. Same is true with subtraction. You want to line up the decimal place. This number now, if you think of it, there's no decimal, so it's absent. So you come from the Atlantic side, and the first non-zero is this 8. So this is your estimated one. When the person had that 3380, they were estimating the 8. And then this other person who had the 45.4 estimated all the way to the tens. So even though this is estimated to the tens, the weakest link in this chain is the tens place here with the 3380. So your answer is only accurate to the tens place here with the 3 in the tens place. So we round there and we get 3330 as our answer. And this way we're not assuming accuracies that aren't there. And that's the point of this. So nobody really likes the addition subtraction. It is a separate rule from the multiplication division, and you just need to keep these straight. Multiplication division is often considered much simpler. So here we are multiplying something that has 1, 2, 3, 4 significant digits with something that has, there's a decimal present. So we start from the Pacific or the left-hand side. The first non-zero is this 5. So this has 3 significant digits. So our answer then has to have as many as the weakest link, and our weakest link here is the 3. So we want an answer that has 3 significant digits. So you can just do this on your calculator and round to 3 significant digits. So that would be 0.0656. In this next equation, we're doing division. And division here, we have decimal present coming from the Pacific, 1, 2, 3, 4. This has 4 significant digits. 32 has just 2 significant digits. So when we do this on our calculator, we want to make sure we end up with 2 significant digits. So we round to this place here, the 21. So our answer is 0.00021 liters. All right, so keep in mind that addition, subtraction, you're going to want to line up those decimals and just stop calculating wherever the least significant place is, which is different than when we do the addition or the multiplication division. where you just count the significant digits and make sure your answer has as many as the fewest. Right, now percent error, we talked about this. The percent error is the degree of inaccuracy, or basically how far you are from the actual. The lower the percent error, the closer your results were. And the formula for this is actual minus experimental over actual times 100%. The experimental you get from the lab, and the actual or accepted value is the true value, which you get from a reference or a hardware store. I don't know if you understand that joke. So a student works in a lab finds the boiling point of a covalent compound. They find it to be 123. So this number here, why can't I ever find my thing? There it is. So this number here is from the lab, and then the reference boiling point is 127. So what are they going to do for their percent error? They're going to take the absolute value. By the way, I meant to mention that this is absolute value. You see these little lines here? What that means is you want it to be always positive. So it's always, oh no, he's writing. Look at that. It almost looks decent. Always, I'm going to stop and just say positive like that. All right, so it's always positive. So 127 minus 123. So the actual reference minus the one you figured out in the lab. And you want the absolute value of that. And divided by the one that you got from the reference, which is 127. So that comes out to 127 minus 123 is 4. That's already positive, so it's good. And 4 divided by 127 turns out to be in the ballpark of 0.003. 003. And then when you multiply that, 0.03 rather. My bad, 0.03. 0.03. And then when you multiply that by 100, you get 3%. So the error was 3%. And that didn't look so bad, if I may say so myself. So another example we did of this was when we did the lab where we were taking Erlenmeyers and trying to determine how they weren't accurate when you add them with water. We were shooting for 65 milliliters each time in that lab. So the actual would be 65, and I asked you to calculate the percent error. So if you got in your lab that when you combined what you thought was 65 milliliters through an Erlenmeyer flask to be something like 58 milliliters, then that is the experimental. So you do 65 minus 58, and my good vibes are over. Watch this, kids. I'm going to do this. I'm going to do this. Discard. I'm going to do this. So 65. Nope. Not going to do a thing. My computer is acting up recently. All right. So apparently I cannot edit my own lab thing. Here we go. All right. So that would be 65 minus 58 equals, so you got 58 in the lab, 65 is what you were shooting for, and that was actually 65.0. True. So let's say you got 58.5, just because that was what we do. Absolute value, so you keep it positive, and that becomes 6.5. And you divide that by the what you should have gotten, which is 65, and then that equals a 10% error. Look at that, Mr. Roach can do that 10% error. All right, so that's an example of that. Moving on. Then we talked about this density, and you did this wonderful FET. Let me not do that right now, but we did this wonderful FET. Actually, I am going to do that right now because I don't think you all did it as well as I wanted you to. So here we go, FET webpage. All right, and the point of this was that if you have a block and you increase the mass without increasing the volume, you can get it to a point where that block will sink. And if you increase the volume without increasing the mass, you can get it to a point where that block can float. But the issue was if you had wood and you tried to add mass, the volume would keep getting larger with it, so it never ever sinks. And if you go to brick and you try to make that float by decreasing the mass, the problem is the volume always increases as well, so that it never wants to float. That's what you should have learned. And that it has to do with density. So all these were equally as dense. That's why they didn't sink, even though they're different shapes and different weights. They all have the same density. All right, so enough about that. Now, density is equal to mass over volume. And we will ask you all sorts of things, like given the volume and the density, what's the mass? Or given the mass and density, what's the volume? And so last year, a student let me know about this triangle, which was very helpful. And that shows that density, which is here by D, is equal to mass over volume. So these two are related by a division thing, mass over volume, right? That's a divided sign thing. And then likewise, volume would equal mass over density. So that's a divided thing, but also shown by the fact that they're over each other. And then mass is equal to density times volume. So that is a multiplication thing because they're not over each other, they're next to each other. So mass is given in the units of grams or kilograms. Volume is given in the units of milliliters, liters, or centimeters cubed, as circled there by your teacher. And what does centimeters cubed mean? So centimeters cubed means if you think of a 3D object, then if we measure this as centimeters and this edge is centimeters and the height is centimeters, then the volume of that is the width times the height times the length, or the width times length times height, however it is you want to talk about it. So that means centimeters times centimeters times centimeters becomes centimeters cubed. And it turns out that 1 centimeter cubed is equal to a milliliter. So that's a nice thing for you to know, that 1 milliliter equals 1 centimeter cubed equals 1 centimeter cubed. All right. I can just think of how Khan Academy started like this in his basement at some point. All right. So here's an example. We have 35 grams of lead and we displace volume of water. Now remember, and we're actually hopefully going to do this lab Monday, where we're going to drop pieces of things in the water, see how the water level goes up, just like we did on the FET. And so you have a weird shaped piece of lead, but you drop it into a graduated cylinder and the graduated cylinder volume increases by 2.5 mils. The question is, what is the density of lead? So if you remember from the triangle, density is equal to mass divided by volume. So our mass is 35 grams, and that has 3 significant digits because somebody went through the trouble to figure out that 0.0. And we're going to divide it by, and that should be a grams. There we go, kind of. And it's divided by the 2.50 milliliters. And that will give us a density then of 35 divided by 2.5, which is 14. But 14 only has 2 significant digits, and we have 3 here and 3 here. And as we just learned, you need to have 3 significant digits because that's the least accurate of either of your inputs. So it's 14.0 grams per milliliter. And that is the units of density. So now gold has a density of 19.3 grams per centimeter cubed. A cube of gold measures 2 centimeters on each edge. What is the volume of the cube? So the volume will equal the length times the width times the height. So that's 2 centimeters by 2 centimeters by 2 centimeters. Since it's a cube, they're all the same. And that comes out to be 2 times 2 is 4, times 2 is 8, which is 8 centimeters cubed is your answer for the volume. And now with that volume, you can figure things out. Whew, that is not pretty. How about that? There we go. 8. Nope. And now it's falling apart. All right, 8 centimeters cubed, because it's length times width times height. All right, so you were hopefully able to do some of those problems that I gave you, and we'll go over that on Monday. Here are just some densities, so you can see when densities are light, things like cork, floats in water, has a very light density. Ice has lower than 1 density because it floats in water as well. Butter would float in water. However, sugar, bone sinks in water, kids. Copper, lead, all these other ones are more dense. You should know that water here is about 1. I don't know why it's not 1, but we usually say water is 1. So that's one thing you should know as well. And then we'll deal with graphs later. So there it is, folks. My last video for this unit. And thanks for listening. I will see you on Monday.